Hello and welcome to MT3. In this recording tutorial, we will look at what happens when you change a basis in a vector space. And this leads to a concept called the Similarity Transform. Now, you will find this discussed in Riley, Hobson and Ben's 8.15. But I will be giving you a few more details which are not explained uh, clearly enough in that particular section. Okay, so here's the idea. You've got a vector space, in this case a two-dimensional space spanned by E1 and E2. These could be any basis vectors. They don't need to be orthonormal. And the idea is that under some transformation, linear transformation S hat, you transform this basis set into another basis set, E1 prime and E2 prime, in the same vector space. It's still two dimensions. Now, because it's still two dimensions, we'll see that you can also transform back, meaning there's a one-to-one mapping between these basis vectors and those basis vectors, so you can then go back with an inverse transform using S hat inverse. Now, this is important. So we will always take it for granted that in this change of basis, the transformation, the linear operator which takes you from one to the other, is invertible, and you can always come back. Now, putting this more mathematically, it looks like the following. So under this S hat transformation, our basis vectors EI become EI prime, so E1 becomes E2, so E1 becomes E1 prime. And this is a linear operator, so we know from our treatment of linear operators that the action of S hat on EI is written in terms of the elements of the S matrix. So this has become the sum over J. We still have the same dimension of the space everywhere, and this result, this vector EI prime could be regarded as a vector in this space, in which case it could be expanded in the basis set of this space. So we write the EI prime, which is equal to S hat operating on EI, and that is a linear combination of the original basis set where these are the coefficients. So in other words, we know how to write EI prime in terms of the original basis set. Now this stems from the definition of a linear operator. Now this, I said this is invertible, so S hat inverse exists, and we can therefore write the EI, this is the EI here, basis vector, as written as it's S hat inverse operating on EI prime. And since this is again a linear operator, we can write EI as a vector in this prime space, and that is written in terms of these coefficients of the S inverse matrix, and then you have the primed basis vectors here. Now all this is just consequence of how linear operators act, and the only assumptions we have made is that this is an invertible process, and that preserves the dimension of the space. Okay, so we are not transforming our space from a two-dimensional space into a one-dimensional space. We are keeping the same dimension. Okay, now there's one statement I'm going to make, and then we're going to prove it. So if S inverse exists, that means if this reverse transformation exists, then if the EI basis is linearly independent, which is what we always assume for a basis set, then so is the EI prime basis. Basically, both of these are linearly independent sets, and that should hold only if this S inverse exists. Alright, so in other words, the S transformation does not change the dimension of the space. To put it another way, if we have a linear transformation S, and if its inverse transformation exists, then the dimension of the space does not change on the action of this S. Okay, and let's prove it. So the proof goes as follows. Let's think back at our definition of linear independence. We say that a set of vectors is linearly independent if, let's remind ourselves, so if you try to make a linear combination like this, so J goes from 1 to n of A, J, E, so I'm referring to this prime set here, if you set this to be the 0 vector, then this set will be a linearly independent set if the only way you can do this is if the only way this is possible is if all AI or AJ, I called it there, doesn't matter though, are 0. Alright, so that's would be okay. So if the only way this is possible is if all the AJ are 0, then this set of EJ prime vectors is linearly independent. Okay, we know that. Now I need to prove that this set is linearly independent. So what we're going to do is we're going to assume the reverse. Okay, so assume that there exists some AJ not equal to 0 such that the 0 vector is equal to j is 1 to n AJ EJ prime. Alright, and we're going to show that this is false. Okay, so let's see how we do this. So let's start with put the 0 vector over here, and that's equal to the sum j a j e j vector prime. Now we know how these EJs are related to the EIs because that's through this operation here. So if I for the moment call this a j here, so the EJ prime would be related to the EJ vector through this S transformation. Okay, so let's use that. So we know that EJ prime is equal to S hat operating on EJ, and that is given by the sum of what's it? So let's put the sum over k over here, and this would be S. Let me get the order right. So we will have an E k here, and the first index is k, and the second index will be the j. That's the order in which we defined the matrix elements of a linear operator. Okay, so let's put that in. So we know this here. So we put that in here, and then we'll have the double sum j. Then we have the AJs. Then we got the sum over k. Now both sums go from 1 to n, so I'm going to skip the limits here. Then we have the skj ek. Alright, now we do our usual rearrangement step. I have a k over here, so I want the sum of k on the outside. So this is equal to the sum over k, and then in parentheses the sum over j, and then we have the skj aj, close the parentheses, and then we have the ek. Okay, now what we've got here is we've got this is a scalar, right? I mean, this thing here in the sum here is a scalar, and what we now have is we've got a linear combination of these ek vectors, and we've said that that's equal to the 0 vector. I need a few other pages here, so let's put them in there. Okay, so what we have shown is therefore the 0 vector is equal to, if I call these scalars, they depend, we are summing over j, so they depend only on k. Let's call them bk. We've got this is equal to the sum over k, bk, ek. But the set of vectors ek or ei, doesn't matter, is linearly independent. This was given to us. Therefore, the only way that can happen is if each of the bk's is 0 for all k. Now what this means then is that the bk, remember, is the sum over here. So we have the sum over j s, let me get the order right. It's skj, aj is equal to 0 for all k. Okay, let's write this. I mean, this sum here is simply a matrix times a vector, right? I mean, so what we, if you combined all of these, for each of these k's, if you combine these results into a matrix vector form, what we can do is simply write it as the matrix S times the vector A is equal to 0, the 0 vector. And now is here where the interesting thing comes. Now we are told that S has an inverse. So we know that there exists S inverse. So what we do now is apply S inverse to both sides. So therefore, what we can do is apply S inverse to both sides, and we get S inverse S A is equal to S inverse and the 0 vector, which of course is just equal to the 0 vector. This gives us the identity, and the identity times a vector is just a vector itself. So therefore, the vector A is equal to the 0 vector. But this is a contradiction, because we assumed at the start that some of those AJs are not 0. So the vector A cannot be the 0 vector. So this is a contradiction. And it's sometimes written like this, with two arrows facing each other. And therefore, we must have A is 0, or AK is equal to 0 for all k. That's the only way you can satisfy everything. So this assumption is wrong, and what that means then is that this is the only solution we can have, and therefore the set of vectors Ej prime is linearly independent. Therefore, if S hat inverse exists, i.e. if the matrix S inverse exists, then the Ej prime basis is linearly, or set of vectors is linearly independent. Alright, good. So that's one important result. Let's now move on to something else about similarity. Now we haven't yet gotten similarity transforms. Let's see what they are. So what is a similarity transform? This is important. So okay, so now what we're going to do is look at the action of some linear operator A on X. So if A is a linear operator, then a vector Y is related to a vector X, let's say, through the action of this linear operator. I've written it down in matrix form. In operator form, this would be the operator Y is equal to A hat operating on X. Yeah. Just to remind you, to get to the matrix form, you need to introduce a basis set. Okay. Let's say now, so this is in one particular basis. So this is in the basis EI, we have this. Now what if you change your basis? So what if we go from this basis to another basis, EI prime, through some linear operator, invertible linear operator S. So we will make sure it's invertible. There's also an S inverse, which takes us back. The question now is, okay, so if you go into this basis here, everything is going to change. The basis representations of these objects will change. So we will have some y prime is equal to some matrix form of A of the operator A, which will now be A prime, and then we will have a vector x prime. And we would like to know how are these components of the primed vectors related to the components of the unprimed vectors. Or more precisely, how are the components of y prime related to the components of y? Okay, so that's the problem we are trying to solve. And what we are going to end up with is show how A prime is related to A, because that's going to make all the relations pretty clear. So first of all, the components of y, and actually that's what I really want to do. So let's state the problem here. This is the main problem. How is A prime related to A? Okay, so that's the question we want to answer. So let's put on what we know. We know how y prime is related to y and how x prime is related to x. So the y prime, oops, that's a vector, not a matrix, is related to y through this operation S. Now, and this is a vector y here. Just a quick pause. Okay, I'm glad I paused that because I realized I hadn't shown this. So we need to show this. What is the relation of A prime to A? But we need to first show that the components of the y prime vector are related to the components of the y vector through this kind of a relation, and also that the same holds for Sx prime. So we need to show these results before we can show how A prime and A are related. All right, so let's start with the vectors themselves. So let's take a vector x. In our space, we introduce a basis set EI, and we know that we can write x as a sum I goes from 1 to n of the xi, those are the components, and then the basis vectors EI. Okay, now we know that when we make a transformation and we go into the primed space, then the EIs are related to the EI primes through this relation. EI and the EI primes are related through this relation. So if I wanted to know what the components of x was in the prime space, we'll start from there. We should be able to relate them to the components in the unprimed space. So that's how x looks in the unprimed space, and here's how x will look in the prime space. So in the primed space, we'll have a prime there, and we will have x is equal to I goes from 1 to n, I call it a prime here, of xi prime ei prime. Now we know that the EIs are related to the EI primes are related to the EIs through this relation here. Now let's see if I remember it. It's up here. EI prime is equal to, this is the relation. So we have Sji Ej. Let's go back here and put it in there. The sum over j, Sji Ej. So let's put that in, and what we get is the sum over I, then we have the xi prime, then we've got the sum over j, and Sji Ej. Now we reverse our sums. This is quite a common operation. J, and then we have the sum over I, Sji xi prime, and then we've got the Ej vectors there. Okay, and now if you compare this with this, remember these two vectors x are the same vectors. We're just representing them in different basis sets. Therefore, these components have got to be the same. So therefore, we must have xi is equal to the sum over I sji xi prime. Or to write it in kind of vector form, we can regard these components as a representation of each of the vector x in each of these basis sets. We can write this as the vector x is related to the x prime vector through this multiplication. And since S inverse exists, we also have the reverse. X prime is equal to all right. Okay, I just realized I'm being a little sloppy here. If you go back to this this part of the proof, I wrote the vector x in terms of the EI basis. That's correct. And then I called and I said in the E prime basis you will have x prime is equal to this. Now I shouldn't have done that. In fact, I'm going to continue saying that this is the vector x, just re-expressed in a different basis. So it's the same vector x. It's not an x prime vector expressed in this basis. And here's where my notation is kind of not good. You know, in a way, what I want to do is to say that this abstract vector x, when written in this basis, can be represented through these components. And this abstract vector x, represented in another basis, gives you a set of different components. Okay. So I mean, perhaps I'm not being completely clear here, but I hope you understand what I'm trying to say, and if you don't, bring it up in the tutorials. So what we now have are these extremely useful relations which relate um, the column vectors x and x prime, which are just representations of this abstract vector x, and these are the column vectors x and x prime, which is what you'd get if you changed your basis. This would be the column vector of the vector x in the EI basis, and this will be the column vector of the vector x in the EI prime basis. And these two are related through this matrix S, which is the linear operator, the invertible linear operator. And because it's invertible, we have the S inverse matrix, which relates x prime, the column vector x prime, to the column vector x. All right. And the same holds for y, right? I mean, so the same will hold for y. Therefore, I think I've not got that right. We should have y is equal to S y prime, and y prime is equal to S inverse y. Okay, so now we have proved one of the results we need, and now let's see what happens to operators. So put a line there. Okay, now what about operators? So we know that for an operator A, we have y is related to a column vector x through this relation. Yeah, and what we want to know is how is this related to if you change your basis and you get the y and we write this in terms of the prime basis, everything gets primed. Then how is A related to A prime? All right, that's easy enough. Let's start from either one of these equations and use these relations here to see if we can come up with a relationship between A and A prime. Let's take the primed relation. So y prime vector, column vector, is equal to A prime matrix times x prime. But we know that y prime is equal to S inverse y. So let's put it. Therefore, S inverse y is equal to A prime, and x prime is S inverse x. Alright, now let's multiply by S on both sides from the left. So we have S times S inverse y is equal to S times A prime S inverse x. Now we know that S times S inverse is the identity, so what we get then is that y the column vector y is equal to S A prime S inverse x. And now if you compare it to this relation here, what we see is that this product of three matrices must be equal to the A matrix. So therefore, the A matrix is equal to S times A prime times S inverse. Or, and I'm going to leave this to you to show, so show this, or A prime matrix is equal to S inverse A S. So we go from the unprimed, to find out what happens to the A matrix when you change your basis, you apply this transformation. The S inverse times A times S gives you the A matrix in the prime basis. And this is called a similarity transform. Okay, I'm going to pause this here and then we look at some properties of this transform. Okay, now for some properties of similarity transforms. You'll find these in Riley, Hobson and Benz, but let's look at them over here, perhaps in a slightly different way. The first is that similarity transform, so if A prime is equal to, the matrix A prime is equal to S inverse AS, then the determinant of A and A prime are the same, so determinants are preserved by these transformations, the trace is preserved by the transformations, and in fact the eigenvalues of A and A prime are the same. This is going to be very useful in what we're going to do next. In fact, they're all very useful. And what this is a statement of effectively is that they share the same secular equation, or in other words, the determinant of A minus lambda I is equal to the determinant of A prime minus lambda I. So here's how the proofs go. I'm going to be pretty quick because by this stage you should be getting used to the idea of actually showing things like these. So for number one, we start with the determinant of A prime. Well, that's the determinant of S inverse A S, and these are all matrices. Now we know from our formulae for determinants, which you have to go back a few lectures, or that the determinant of two matrices A and B is equal to the determinant of BA. Now this can be generalized to any number of matrices. I'm going to leave this to you to figure out how to do it, but you have seen this often. And what this means is that in principle you can cyclically move them around. It's always cyclic. It's anything that's not cyclic, it's not allowed. So this is equal to the determinant of S. I'm going to move it this way. So let's just draw this. We are moving this here, and these guys all go one step that way. So we get the determinant of S, and then S inverse, and then A, and you can see what's happened here. This is simply the identity. Therefore, this is equal to the determinant of A. Proof done. Okay, next, the trace. You're going to see how this works. I'm going to leave the trace formula to show this for yourself. So show this. Okay, now let's have a look at the third one, the eigenvalues. So we need to show that the secular equations, so these determinants are in fact the same. And as before, we're going to start from here and show that it's equal to this one here. Okay, so this is number 3. So start with A prime minus lambda I. Here. By the way, you notice what's happened here. You might be asked a question like this: show that the eigenvalues of A and A prime are the same if A prime is a similarity transform of A. Now you need to translate that into mathematics, and the mathematics says that if these eigenvalues are the same, they must share the same eigen secular equation or characteristic equation, and that means that this has to hold. This kind of translation of an English sentence into mathematics is something you need to figure out how to do. So we start from here. we know what A prime is. It's equal to S inverse A S minus lambda times the identity. Now the identity itself can be written as S inverse of S. So we put that there, and we can leave the identity in there. Alright, now you can see there's an S inverse S on both of these. That's what I wanted. So we write this as S inverse parenthesis the matrix A minus lambda I and S. Now you can see where this is heading, because what we now do is call this matrix B. So this is equal to the determinant of S inverse B S, and now we can use cyclic permutations. Determinant remains the same. That's equal to the determinant of, in fact, from the previous result, this is equal to the determinant of B, and B itself is this matrix, which is A minus lambda I. Therefore, the circular equations are the same, because from here you will get some nth order polynomial, and the nth order polynomial from here will be the same as this one here. Therefore, the eigenvalues of A and A prime are the same. All right, good. Now we are nearly at the end of this recording. The last thing I want to talk to you about is a special case. The case when S is unitary. That means S inverse is equal to S dagger. Dagger is the Hermitian conjugate, or the adjoint. Now, this is a special class, because what we will show, I'm going to leave some of these to you as an exercise, is that if you start off with an orthonormal basis, so here I've used the hats to indicate that this is an orthonormal basis, then this kind of transformation, this unitary transformation S, keeps the basis orthonormal. So it may rotate itself or whatnot, but it's going to remain orthonormal. And likewise, if you use the reverse transformation, it stays orthonormal. So for this particular case, since S inverse is equal to S dagger, the similarity transformation becomes A prime, the matrix A prime is equal to S dagger AS. All right. Now this has one nice properties. This is the first one. We're going to prove this. If EI hat is an orthonormal basis, then so is EI prime hat. That is, in mathematics, if the inner product of EI hat with EJ hat is equal to delta IJ, then so is the inner product of EI hat prime with EJ hat prime. The another thing is that inner products are preserved. So the inner product of vector A and B will remain the same. It's the same as the inner product of the vector A prime and B prime. Another thing is that if A is a Hermitian operator, then so is A prime. Okay, and this is what I'm going to leave for you. If A is a normal matrix, then so is A prime. And I also want you to think about this. If you prove that this holds, then does it imply result 3? Okay, think about it. So let's just show a couple of these results. So the first one, if EI is an orthonormal basis, then so is EI prime. So the proofs are here, at least to sum up some of these. Number one, let's start, as always, with the primed side. So we consider EI prime, EJ hat prime, and what I want to show is that this is equal to delta IJ. All right, so let's do it. So we know from the transformation that, let's go back a few pages, let's remind ourselves of what we need over here. Here we are. EI prime is equal to S operating on EI, and this is given by the sum. So we need to use the sums now. So go back all the way down. So let's put it here. EI prime is equal to the sum over, I've got J over there, so let's use the sum over K. And we'll have an S K I E hat k. Yeah. Similarly, E hat prime j, we'll have to use a different index. Instead of k, I'll use an L. S L J E hat L. That's all you need to make sure when you write these things down. Just make sure you have different indices in your dummy sums so they don't collide. All right, so now we are in good shape. Let's write this down then as the inner product of this sum, the k sum, S K I E hat k, with the L sum, S L J E hat L. Now because these are the inner product, if you have a linear combination of terms in the inner product, this goes back definition of the inner product, you can pull those linear combinations out, and all you have to do is remember to complex conjugate any scalars that are in the bra side. So this is in the bra side. Therefore, apply. Yep. So this gives us the sum over k, the sum over L. We will have an SKI star. This is in the ket side, no complex conjugation, SLJ. And then you have the inner product of the two vectors, E hat k with E hat L. But hey, this is an orthonormal set, so this is equal to delta KL. And we know what delta, the Kronecker delta does is it sets k is equal to L and collapses one of the sums. So this then becomes, I'll keep the sum over k, why not? And we set L is equal to k and collapse the L sum. So we get SKI star SKJ. And now we write this as the sum over k. I can write this first term as S dagger. And I need to now swap these indices because the dagger includes the transpose. So it will be IK. And the second term, I'll just keep it as the S matrix, KJ. And now this is exactly in the form of A, matrix A times matrix B. We are summing over the inner index. Yeah. So this will be the ijth element of S dagger multiplied by S ij. But S dagger multiplied by S, since S is a unitary matrix, we have S dagger multiplied by S is going to give us the identity. So this is equal to the ijth element of the identity, which is just delta ij. And that we proved it. So that's the proof. Therefore, this is equal to delta ij, and therefore the primed basis ei hat prime is orthonormal. Okay, and that sentence there completes the proof. By the way, you don't just stop there, you have to include the sentence. Let's do one more and then I will stop here. So let's use that to show that inner products are preserved, and I'm going to leave 3 and 4 for you. So prove this. The proof, by the way, is in Riley's book, so have a look there. Let's have a look at number 2. Inner products are preserved. So we need to show this. If we got two vectors A and B, then the inner product of A B is equal to the inner product of A prime B prime. Alright, and just remind ourselves, A prime will be related to A through a similarity transform, and so will B prime be related to B through this transform. Right, so let's start with the left hand side, sorry, the right hand side. So we have A prime B prime. No, these are vectors, not matrices. And that's in the alternative form for the inner product. We can write this as A prime dagger B prime. Okay, I'll show you another way of doing this in a bit. This is equal to, now A prime is this, so we have S A dagger times S B. Well, you can bring the dagger in and just swap the order, so we'll get A dagger S dagger S B. Well, guess what? Since S is unitary, this is equal to the identity. Therefore, this is equal to A dagger B, which is simply the inner product of A with B. Therefore, inner products are invariant. All right. Now, another way of showing this, by the way, so that proof is complete there. And another way of showing this, in case you're curious, so this is, here I've gone from the Dirac form to the standard vector form, and then we've gone back to the Dirac form. Now, is there a way of staying in the Dirac form? And there is one. So Dirac all the way. Here's how it happens. We start off again with A prime, B prime, and this time we don't need the bars because in the Dirac form these are vectors. Well, so that's equal to S, and we can write S in its operator form now because I don't need to, in the Dirac form I don't need to use a basis until the very end, if you wish. This is equal to S operating on A, and we have S operating on B. I don't need this force of habit here. Okay. Now what happens here is the Dirac form lets us move the operators from the browse side to the ket side, but there's a rule here, and here's the rule. Okay, the rule goes as follows: is if you have a vector, an operator, let's see, A in the browse side, then you can move it to the ket side and it becomes its adjoint. And likewise, if you have an operator A in the ket side, you can move it to the browse side and it becomes its adjoint. Okay. Now, if you translate this into the language of we've used over here, where we've gone into this kind of vector, column vector like formulation of the inner product, you'll see that it's the same. I'm going to leave that for you as kind of an exercise to try it out. So here, what we do is we take one of these operators and move them to the other side. It could be either way, it doesn't matter. I'm going to take this guy and move it here. So this would become A S hat dagger S hat B. Well, but S hat dagger S hat is the identity operator. So this is equal to A, the identity operator B, but that's just equal to A, B. That's easy. That's the way you can use the Dirac notation all the way. Now, if you get comfortable with this, and if you start to see that this is in fact completely equivalent to, oops, that was a bit, sometimes it does it, I don't know why. Here we have gone from Dirac, we've introduced the basis, you get column vectors, and in the column vector form, this is the adjoint of a column vector times another column vector. Then you introduce the matrix vector expression there, take the adjoint, and then you swap their order and take the adjoint of each term, and then, this is fine, it works. In fact, it's much better to do this than to go to the index notation, which is what Riley, Hobson, and Benz does. But this is even better if you understood how it works. So I'm going to leave this for you. You don't have to use the Dirac notation all the way. It's an option, but it's a nice option because anyone doing serious derivations in this area will probably use this kind of a procedure rather than the one above. Okay, so we stop here, and these are the exercises which you've got to do. I strongly suggest you do them. You'll find a solution to 3 in Riley, Hobson and Benz. The solution to 4, you should be able to show it using the same ideas as with 3. Think about this question here, and if you have any questions, again, if you get stuck, ask me in the tutorial or some other time. Okay, and that's it for the similarity transform. Thanks for watching.